Welcome back to Algorithms and Uncertainty. Today we will start talking about online learning in worst-case models. What does this mean? Well, we have a bunch of actions we can choose from, and these actions are not equally good. And our goal is to determine which of these actions is the best one, or more precisely, to decide which of these actions to choose. This is somehow similar to what we were doing last time when we were considering this setting where the rewards were determined by probability distributions, but now we'll do more kind of a worst case analysis where the rewards, or in this case now costs, are determined by a hypothetical adversary. To get us started on thinking about such problems and algorithms for these problems, let's consider a very simple motivating example, which is motivated by binary classification. We will have n binary classifiers. And each of them predicts positive or negative when it is given a data point. So this might be, for example, spam classifiers. We give them an email, and then for each of our classifiers we get to know whether it says that this is a spam email or whether this is not a spam email. And now we'll have the following round-based classification problem. In each step, one data point is being revealed. We get to know the predictions of all classifiers. Then we have to predict a label. And then we get to know the correct label. What can you do here? So, based on these predictions that we get in the second step here, we now in the third step have to predict our own label before then getting to know the correct label. What can we do here? Well, let's start with a very simple assumption, namely that one of these classifiers is always correct. What do you want to do? Well, let's talk about the very first step. There we do not know which of our classifiers is correct. We do not know anything about our classifiers. So we get to see all these predictions, and then we'll have to choose one label on our own. And what's the reasonable thing to do? Well, the reasonable thing to do is just to follow the majority of all these classifiers. And this is the following majority algorithm. We let S be the set of all classifiers which have never been wrong so far. And we now follow the advice of the majority in S. Why does this feel like a good idea? Well, we have now this set S of classifiers that have never been wrong. Initially, no classifier has been wrong. Good. Now we'll follow the majority of the classifiers in the set S. And what can happen now? Well, one of two things can happen. Either our classification is correct. Well, great. This is all we want. Or we're wrong. But what does that mean? That means that half of our classifiers that had never been wrong so far are now wrong. Which means that for every error that we make, for every mistake that we make, for every label that we incorrectly predict, the set S halves in size. So we make progress towards our goal of identifying this one classifier which is always correct. Cool. So how many mistakes can we make? Well, initially there are n classifiers. After the first mistake that we make, there are at most n over 2 classifiers which have never been wrong. After the second mistake that we've made, there are at most n over 4 classifiers that have never been wrong, and so on. Ultimately, because of our assumption that one classifier is always correct, this set S will never be empty, so its size will always be at least 1, which means how often can we have the size, if we're starting from n and ending at 1, well, we can have it log n times. And this is the reason why we can observe that if there is a perfect classifier, majority will make at most log to the base of 2 of n mistakes. Fantastic. Now what happens if this assumption is not true? If indeed every classifier is wrong from time to time, how do we then identify the best classifier? Or more precisely, how do we minimize the number of mistakes that we make? This is exactly the kind of question that we would like to answer. Now let's talk about the setting in which every classifier makes a mistake once in a while. Then it surely does not make sense to maintain a set of classifiers which have never been wrong, because we'll just reach the point at which this set becomes empty. And what should we do then? We'll now talk about the weighted majority algorithm, which is similar to the majority algorithm, but it does not exclude a classifier when it has been wrong once, or when it has been wrong twice, or so. What it does instead is it maintains a weight how trustful this classifier is. And if a classifier turned out to be very good so far, it will have a higher weight. If it turned out that this classifier has been wrong very often, then the weight will be very small. So we maintain the weight Wi for classifier I. And we'll set WIT. This is the weight in step T. Or more precisely, it is the weight before step T. Initially, all of these weights are 1. And how big is the weight before step T plus 1? So after step T, we now say, okay, we keep the weight if classifier I is correct in step T. And we reduce this weight otherwise, meaning that if the classifier was wrong. Here this eta is somewhere between 0 and a half. It should not be exactly 0. It should not be more than a half. This is a parameter of the algorithm. And just so that you know, this letter you pronounce eta. Although it looks like a small n, it is actually a Greek e to some extent. Good. Now we have these weights. And how do we now come to a decision? Well, this is exactly what the algorithm name tells us. In step T, we predict the label which is proposed by the weighted majority of all classifiers. Good. So this algorithm actually generalizes the majority algorithm. Namely, if you wanted to see the majority algorithm in this framework, well, actually you would have to now set this eta to be exactly 1, which I excluded by this condition. But for the time being, let's assume what would happen if we were setting eta to be exactly equal to 1. Then initially all weights are 1, and if I make a mistake, then my weight drops down from 1 to 0. Now we are not that strict by saying, okay, now your weight does not drop all the way to 0, but maybe, let's say if eta is a half, then after you've made one mistake, your weight will drop to a half rather than 0. Which means that when we're now choosing our label, which of the labels we're predicting, your prediction will only have half the weight of a classifier which has been correct in the first step. So this was what would happen in the second step. Now, if you're wrong again, then your weight will again drop. It will drop to a quarter. So this is if your prediction turns out to be wrong both in the first and in the second step, then your prediction will have weight only a quarter in the next step. Maybe all of the classifiers are wrong, then, well, all weights drop by the same amount, which relative to each other would not change at all the weights. So certainly we will never reach the point at which there is no prediction anymore, because these weights actually never reach exactly zero. They might get tiny, but this is always a feasible rule for our possible predictions. And now we can also again bound the number of errors that this algorithm makes, namely, what we will be showing is that weighted majority makes at most 2 plus 2 eta times the minimum of all mi plus 2 times ln n over eta mistakes where mi is the number of mistakes of classifier I. So this statement, to some extent, still generalizes the kind of statement that we had before. There we were saying, okay, there is a perfect classifier, which meant that the minimum of these mi would be 0. In this case, we would now have 2 times ln n over eta mistakes that we would make at most. Now our bound is a little different because, well, it's by just only relying on these imperfect classifiers, it is not possible to not make to make only this many mistakes. What we'll have to take into consideration is how good is the best of these classifiers that we are using here. And now this, depends on our choice of eta, but if eta is, for example, a half, then this will be 3 times the minimum number of mistakes that a classifier makes plus 4 times ln n. Good. Is this surprising? Well, I hope it is not super surprising given that you've seen the majority algorithm and what happens there. And now what we'll try to do is we'll try to do the same kind of analysis that we sketched for the majority algorithm. Namely, what is it that we do? We let capital W be the sum of all weights. And by that I mean the sum of the weights that we are using in step t. This is capital W at time t. And what happens to our weights? Our weights are always only reduced. If we go back to our algorithm, here the weight may either stay the same or it is being reduced. This is why the sum of the weights can only reduce. Now what will happen if our algorithm makes a mistake? Let's consider a fixed time step. In which the algorithm makes a mistake. Why is this happening, that the algorithm is making a mistake? Well, it is because the weighted majority of classifiers was wrong. So let capital U, which is a subset of the numbers 1 through n. Let this be the classifiers that are incorrect. In this particular step. What do we have now? We have, of course, that the sum of the weights of the classifiers in U is at least as big as the sum of the weights of the classifiers which are not in U. Sure, because it is a weighted majority, otherwise we would have chosen the other label. Which means nothing but that the sum of the weights in U is at least half of the sum of all weights, which we define to be capital W. And what else do we have? For every I in U, the weight after this step will be reduced, namely by this 1 minus eta factor. And for all I which are not in U, those classifiers are correct, so we will just keep the weight. What does this tell us? This tells us now that the sum of the weights after this step, so before the next step, that's clearly just the sum of the weights that we have in U plus the sum of the weights that we have outside U. This we can now rewrite as 1 minus eta times what we have inside U and just the unchanged weights for everything outside U. And how big is this? Well, on the one hand, we now get the sum of all weights, and then we're subtracting eta times the sum of the weights in U. So this will be no more than 1 minus eta over 2 times the sum of all weights. This is now for any time step in which the algorithm makes a mistake, we get that the sum of the weights after this is smaller than the sum of the weights before this, namely it is smaller by this factor. And this is, I hope, sounds familiar because when we were talking about the majority algorithm, we were talking about how many classifiers do we have still in our set of classifiers which were never wrong. And whenever we make a mistake, this set gets smaller by a factor 2. And now this is the analog of the statement, namely that the sum of the weights gets smaller by this 1 minus eta over 2 factor whenever we make a mistake. So we can indeed bound the number of mistakes in terms of the weights that we have at all times. More precisely, what we have is, if we now let m be the number of mistakes of our algorithm, within the first capital T steps, Then we'll have W at time t plus 1. So after these t steps, what will the sum of our weights be? It will be at most 1 minus eta over 2 times the to the power of m times the initial sum of the weights. And what is the initial sum of the weights? It is n. And so now the sum of the weights that we have eventually is at most this factor to the power of m times n. Now what we'll have to relate this to is the minimum number of mistakes that any classifier makes. And what we have is that the small wi at time t plus 1, how big is this? This is the weight of a classifier after capital T steps. This is nothing but 1 over eta to the number of mistakes that this classifier made times the initial weight. Because for every mistake that we make, we get this factor 1 minus eta. For every step where we don't make a mistake or where this classifier does not make a mistake, the weight remains the same. So this is the weight that we end up with. The initial weight is 1. So this is nothing but 1 minus eta to the power of mi. Now what else do we have? We have that the final sum of the weights is at least, of course, the maximum of all these weights, because all these weights are non-negative. So this is equal to the maximum of all these 1 minus eta to the power of mi, which is nothing but 1 minus eta to the power of the minimum of the mi. And if you now combine the two things, what do you get? We have now that the sum of the weights is at most this much, which takes into consideration the number of takes that our algorithm makes, and it is at least this much, which takes into consideration what the number of mistakes that the best classifier makes. So if we combine the two, then we get that 1 minus eta to the power of the minimum of the mi is at most 1 minus eta over 2 to the power of m times n. Or if we now take the logarithm on both sides, the minimum of all these mi times the ln of 1 minus eta will be no more than m times the ln of 1 minus eta over 2 plus the ln of n. Now this is very close to the kind of a statement that we would like to make, namely we'd like to say that m, okay, you have to realize that those things are negative here, so this is saying something like m is at most something related to the minimum of all mi. And how do we get to the kind of a bound that we would like to use? Now what we'll use is that we can actually approximate the ln that we have in here as follows. the ln of 1 minus z, this is the blue line in this picture here, we can approximate by, well, on the one hand taking just the tangent. This will give us something that is at least as big as the ln, or we can approximate it by this quadratic function, which is this red line here, which will be a lower bound on the ln. So I'm not proving this inequality. I hope that you trust me when you see this picture here, that this blue line is somewhere between this orange and this red line. Here on the right hand side we have the orange line. Here on the left hand side we have the red line. Cool. So how does this help us? We can now bound this term and this term using a linear, respectively a quadratic term. More precisely, what is it that we're getting here? You will use that this is at least minus eta squared, and here this is at most minus eta over 2. So what does this tell us? This now tells us that we're getting that the minimum of all the mi times minus eta squared is at most m times minus eta over 2 plus ln n. And this tells us that m is at most 1 plus eta times 2 times the minimum of all mi plus ln n over eta times 2. And this is exactly the bound that we were claiming. Cool. So how does this work? It's actually not super complicated. Once you keep in mind that this analysis for the majority algorithm was that simple. Here now we have what we had as the cardinality of the set S, so the number of classifiers that did not make a mistake or had not made a mistake up to a certain point. This is now replaced by the sum of the weights. Maybe not surprisingly, because when we set these weights to be 1 for classifiers which were correct always so far and 0 otherwise, so 0 for classifiers which have already made a mistake, then the sum of the weights is exactly the number of classifiers which have never been wrong. Cool. Now we get very similar bounds, namely we on the one hand get that the sum of the weights relates to the number of mistakes that we make, that our algorithm makes. Why that? Because for every mistake that our algorithm makes, the sum of the weights drops significantly. And then we have, on the other hand, that the sum of the weights, the final sum of the weights, also relates to how good any classifier can have been in our set. Because there is one part of this sum is indeed the highest weight, which is the best classifier. Cool, and then you have this inequality, and all you have to do is actually approximate the logarithm by a linear, respectively a quadratic function, and then you're there. So all that we're losing here, or all that is happening, is actually just what is illustrated in this picture. Fantastic. Now the guarantee that we're getting is that the number of mistakes is at most, yes, something like twice the number of mistakes that an optimal classifier makes. But our goal is actually to be much better than this, and this will actually work. We will now be able to show that we can get, at least asymptotically, that the number of mistakes that we make is no larger than the number of mistakes of the best of our classifiers. By introducing a slight twist into the weighted majority algorithm, we'll now be able to get a much better guarantee. Namely, so far our guarantee was something like, okay, we make at most twice the number of mistakes that the best classifier makes. Now we can get this down to asymptotically we make only the same number of mistakes that the best classifier makes. And what's the change in our algorithm? Let's go back to the weighted majority algorithm. We actually keep everything the same here. So we'll again maintain weights just the same way. But then the way we predict the label is different. Here we were saying, okay, now predict the label which is proposed by the weighted majority of all classifiers. Now what we'll do instead is, rather than picking this one label which is predicted by the majority of all, or the weighted majority of all classifiers, we'll draw one of the classifiers at random and just use their prediction, whatever this classifier predicted, this single classifier predicted. And where does our probability distribution come from? It comes from these weights. So initially all the weights are the same. We would just draw one of the classifiers uniformly at random. Now, some of the classifiers are correct, some others are incorrect, which means that we have the weights of the classifiers which are incorrect. And this now we use as the probabilities. So in each of the steps, we'll choose a classifier with a probability proportional to its current weight. So divide the weight by the sum of the weights, and this will give us the probability that we want to rely on this particular classifier in this current step. This is the randomized weighted majority algorithm. But what you'll now see is that this algorithm doesn't need at all that those are binary classifiers. This could also be some other things, because we're not actually relying on any majority vote whatsoever. We're just asking one particular classifier, what do you say? And therefore, this setting actually, or we can now generalize our setting vastly. Namely, what we'll only talk about now is, rather than talking about classifiers and binary classification and so on, we'll only talk about experts. Each of these experts gives some advice, and we will follow one of the experts' advice. So this is the following expert setting, which generalizes the setting that we've talked about so far. Namely, we have n experts, and in each step we get a piece of advice from every expert. We will follow one expert's advice, and then we get to know how good the experts were in this particular step. And more precisely or more mathematically, we'll do the following. There is now a sequence of cost vectors L1 through LT, and LIT is somewhere between 0 and 1. This is the cost of expert I in step T. And in step T now the following happens. We will choose one expert IT at random from some probability distribution, and then we get to know all the costs of all experts and we incur costs L subscript IT, so depending on which expert we chose in the first step. How does this generalize the setting that we had so far? Well, if we now were saying the cost of expert I in step T is whether this classifier is correct or is incorrect, then we would just say the cost would be 0 if the classifier is correct, it would be 1 if the classifier is incorrect. And now let's generalize the algorithms that we had so far. Let's talk about the algorithm multiplicative weights or hedge. There are multiple names for actually the same algorithm. I usually call it multiplicative weights. Some people also call it hedge. The idea is always the same. Maybe you'll find this differently in the literature, but as I was saying, there's no big difference between all of them. So what we'll now do is actually the same as what we were doing with the weighted majority algorithm, or also with a randomized weighted majority algorithm. Initially, we set our weights of all experts to 1. And at every time t, we'll do the following. We let capital W be, as before, the sum of the weights of all experts. And now we'll choose expert I with probability PIT, which is equal to WIT divided by capital W. So the probability is proportional to the current weight, because the denominator is the same for all experts. And now we'll update our weights exactly the same way we were doing this before. Well, not quite exactly, because now these costs are not necessarily equal to 0 or 1, they might be somewhere between 0 and 1. And this is why we'll do the following. We'll multiply this by this 1 minus eta to the power of LIT. How big is LIT? LIT is somewhere between 0 and 1. If this is 0, then we keep the weight unchanged. If it is 1, then we multiply it by 1 minus eta. If it is somewhere in between, well, we're doing something in between. And what we can show now is the following. We can show that this multiplicative weights for any sequence of cost vectors in 0, 1 guarantees that for all experts I, the cost that our algorithm incurs is no more than 1 plus eta times the cost of expert I plus ln n over eta. And the first thing here, this is the expected cost of our algorithm. So take the sum over all time steps, take the sum over all experts. What's the probability that we choose expert I in step t times the cost of expert I in step t? And the other thing is LIT, capital LIT. This is just the overall cost that expert I incurs. Good. So, first of all, this algorithm, I hope you realize it's just a generalization of randomized weighted majority. It's just a slight modification of the weighted majority algorithm, where we now use this randomization. It is more general in the sense that we now have the general costs for experts rather than having only this correct or incorrect. But that's the only modification that we make. Now, what we'll be able to show is that the expected cost that our algorithm incurs, so take the sum over all time steps, take the sum over all experts, what's the probability that we choose the expert, times the cost of this expert in this time step. And this is at most 1 plus eta times LIT. LIT, this is the, or capital LIT, is the sum of all small LIT, the summed up cost of expert I, plus ln n over eta. So this guarantee is very, very similar to the one that we derived for weighted majority, except for the fact that there we had this factor 2 floating around here. Both here and here we had a factor of 2. Now the advantage is that this factor 2 now vanishes. Other than that, I think the bound is just exactly the same. And what consequences this has, we'll see after we've proven this theorem. So let's try to prove this theorem. And how should we approach such a proof? Well, what we'll again do is, how does the sum of the weights change? Capital W, sum of the weights after step t, or before step t plus 1, is nothing but the sum of the weights and how does the sum of the weights change? It is now the weight before step t times 1 minus eta to the power of LIT. Now we'll simplify this expression here. Namely, what we'll use is that for all z, we have that 1 minus eta to the power of z is at most 1 minus z times eta. Where is this coming from? It's actually nothing super surprising, because this here is 1 minus eta to the power of z. This is the orange line that we have here, and this is 1 minus z times eta. This is the red line that we see here. For z being equal to 0 or 1, we have equality. And for anywhere in between, the orange line is below the red line. This is because this is a convex function. So as we have a convex function here, the connecting straight line is always above the respective function graph. Cool. So this certainly lets us upper bound this quantity here by 1 minus LIT times eta. And so, what do we see here? It is capital W, or let me maybe make a step in between. We here get the sum of all weights minus eta times the sum of all weights times the respective costs. And how big are these things? This here, this is nothing but capital W. And how big is this? This is something we'll have to talk about. Let now be L T be defined by the following. Take the sum of all PIT times LIT. So this is how big? This is the cost of the algorithm, or more precisely the expected cost of the algorithm in step t. Now we can also write this as follows. We get that this is small w divided by capital W times LIT. And how does this help us? here, this quantity now we see, okay, this is actually nothing but capital W times L log T. So what we're getting to is the following. The sum of the weights after step T is, at most, the sum of the weights before step T minus eta times the weights before times the cost of the algorithm in this step. And this is actually extremely similar to what we've seen before. Namely, before we had that the cost of our algorithm was either 0 or 1 in a step. And then we said, okay, whenever the cost is 1, so whenever we make a mistake, the sum of the weights decreases by a lot. Now here, the expected cost of our algorithm might also be somewhere between 0 and 1, and somehow this is generalizing this kind of a statement. Namely, that the sum of the weights after step T is bounded by something that depends on the sum of the weights before step T times 1 minus eta times the cost that we are incurring in this particular step. Cool. So if we now combine all of this, how big is the sum of the weights that we end up with eventually? This is at most the sum of the initial weights times the product of all these terms. And how big is the initial sum of the weights? It is n, because each initial weight is 1. What else do we know? We know that the sum of the weights after step T is at least every individual weight. And an individual weight we get by the initial weight times by how much is the weight being decreased over time. It is these 1 minus eta to the power of LIT. The initial weight is 1, so what we're getting here is 1 minus eta to the power of the sum of all these LIT, which we called capital LIT. Let's take a breath here. We've seen some upper bound on the sum of the weights, some lower bound on the sum of the weights, exactly the way we were seeing this also with the weighted majority algorithm. Namely, the upper bound on the sum of the weights somehow is connected to the cost that our algorithm incurs. The lower bound that we have on the sum of the weights is somehow connected to the cost of an individual expert in this sense. In this case, or before we were talking about classifiers, but these classifiers have now been generalized to experts. And now we'll do exactly what we were doing before, namely we'll combine the two things, we'll take the logarithm and use the exact same inequality that we were using before. So if we combine the two, what is it that we're getting? we get that 1 minus eta times LIT is at most n times the product of 1 minus eta times the cost of the algorithm in step t. Now take the logarithm on both sides. We get LIT times the ln of 1 minus eta is at most. And now what we'll get is here the sum of all 1 minus eta times the cost of our algorithm. Of this, we are taking the ln plus ln of n. And to bound these two things, these two logarithms, we'll use the same inequality that we had before. What did that say? It said that minus z squared is at most ln of 1 minus z is at most minus z for all z in the interval from 0 to a half. Which tells us that we can upper bound this here. Sorry, we can lower bound this by saying, okay, this is at most minus eta squared. And this here, this is at most minus eta times the cost of the algorithm in this step. Now, what is this telling us? This is telling us that LIT times minus eta squared is at most minus eta times the sum of all LLT plus ln n. Now divide this by minus eta, then what we get is that LIT times 1 plus eta is at least the sum of these LLT minus ln n over eta. And this is exactly what we want, namely that the sum of these LLT, which is exactly the expected cost of our algorithm, this is at most 1 plus eta times the LIT plus ln n over eta. Good. So this proof is again a little more complicated than the previous proof, but I hope you realize it's always the same idea that we're using. The idea is still the same as the idea that we were starting from, how we were analyzing the majority algorithm, namely, what does it mean that we make a mistake? That was the question there. Now the question is, where can we see how much cost we are incurring throughout the sequence? And we're seeing, okay, this is again related to the sum of the weights that we have. And also the sum of the weights relates to what you can ideally do, what the cost of the best expert is. and then plugging these two things together, and then we again use this crucial inequality that somehow we can approximate the logarithm by this linear, respectively quadratic function to then get the bound that we need. And interestingly enough, here this seems to be the point where we're losing things, where we're losing something, because we somehow have this here as a quadratic function. On the other hand, we have this as a linear function. Probably this the bound would be much better if we had equality here on both sides, but well, that's just not true. So this is where we are somehow where we're losing this log n factor, or where this 1 plus eta factor is coming from. And this n, where is this coming from? This was coming from the fact that we had the sum of, we were comparing the sum of all weights, which was n initially, to a single of the weights, which was 1. So this is where this n is coming from. This is initially the ratio will be n, so the logarithm of the ratios will be ln n, and this is where this is coming from. Good. Now we've analyzed this algorithm. Let's now, in the next step, talk about what this actually means, and that this is actually a fantastic result. This is once again the theorem that we've just shown, namely that the expected cost of the multiplicative weights algorithm is at most 1 plus eta times the cost of any expert plus ln n over eta. What does this mean? Well, for I, we can just set, I to be the best of all our experts. Then the cost of our algorithm, the expected cost of our algorithm, is something times the expected times the cost of this best expert. Now, what we can do is we can still set this eta. And if we now set the eta as follows, namely to square root of ln n divided by capital T, then what we'll get is that the cost of our algorithm will be at most, well, 1 plus eta times the minimum of all costs of any single expert plus ln n over eta. So this will be cost of the best expert plus ln n divided by t times the square root of this times the cost of the best expert plus ln n times square root of t over ln n. And what's the cost of the best expert? This is at most t, because every expert costs at most t in every step. So this here will be at most the minimum of all experts' individual cost plus 2 times the square root of t times ln n, because both of these are at most t square root of t times ln n. And if we now call, and now we define the regret of our algorithm to be exactly the cost that we incur minus the cost of the best expert. This is what we call not only the regret, but the external regret of our algorithm. And what we'll see is that in this case here, the regret or the external regret will grow sublinearly in capital T. So the more steps we have, the smaller this becomes compared to, or the average contribution of this per step gets smaller and smaller. And we say now that if the regret grows sublinearly in T, then we have a no external regret algorithm. So our algorithm is indeed a no external regret algorithm because the additive part that we're getting here is growing only sublinearly in T, and the meaning of this is that the average error that we make per time step is vanishing if the sequence gets long. So if the sequence gets long, then we have only a square root of ln n over t additional error per step compared to the best expert. Cool. Over the next lectures, we'll see more no-regret algorithms. We'll see them, for example, in the setting where we have reduced feedback. We'll then also again see that these square root t bounds, they will keep repeating for good reason, because this is the best that one can hope for in this setting. So indeed, this algorithm is also optimal, as we will prove. And then we'll also generalize the setting even beyond the expert setting. So this is what's coming up. There's one small remark I'd like to make at this point, namely in the lecture notes you'll see that you can, instead of using this eta parameterization, you can choose this slightly differently, namely that you use an exponential function. Sometimes you'll also find this as the way that the multiplicative weights or hedge algorithm is written, that you'll see an exponential function floating around there. We were now using this 1 minus eta something. Eventually they are just interchangeable. It's just a different way of writing the exact same algorithm. Cool. This is it for today. I hope you enjoyed this. At least I do. Please do let me know if you have any questions, and I hope to see you next time. Stay safe. Bye.